week. Now we are in the last lap of the training. So at this moment, I would like to call upon our facilitators, Professor Balaba and Dr. Namaweje, to take over. Professor Balaba, the floor is yours. Thank you.
Thank you, Dr. Runyararo. Good morning, participants. This is our last day of training. We are going to have Dr. Helen start with logistic regression and the exercise that she sent. Then I'll come in with the factorial split plot, and if time allows, repeated measurement. If not, then we shall see. Thank you. Let me give the floor to Dr. Helen to start immediately. They say no mic. Is my volume low?
No, we can hear you very well.
Oh, okay. Somebody is saying no picture. Oh, don't worry. Okay, if you want to see me.
We want to see you.
There you go. Okay, thank you very much. Let me let Dr. Helen
Helen, maybe you can disconnect the microphone and then you use the computer directly. Alternatively, you can use the one for Susan.
Hello, participants. We are sorting out a small technical error and will be, oh, you can't hear me. Okay, I had muted. Hello, can you hear me? Okay.
Yes, we can hear you.
Yeah, we are sorting out a small technical error on her laptop, then we'll be with you like in 2 minutes.
Hello, can you hear me now?
Yes.
Okay, fine. Let me use your.
First, go to the exercise.
Okay. I'm sorry. We are so sorry about the technical issue, but right now we can proceed. Welcome once again. By the close of yesterday, I'd left some assignment to exercises for you to do. Now, right now, what we are going to do, I want two people to share with us if they manage to do the exercise, the one for model building, and then if you manage to test for chi-square. We do it for the first, for example, like 10 to 15 minutes, and then I'll move on to logistic regression. Then after the logistic regression, Professor Susan will come in to do other bits for experimental designs. So are there some members who are willing to share? Are there some participants who managed to do the assignment and are willing to share with us such that we are able to guide you very well? If you are interested, just type in the chat your name that you're interested to share, or you can raise your hand and then David will.
We have the first participant called Achor.
Okay.
Amos. And there is also Sarah. So those two participants can start. Sarah and Amos.
Okay, thank you so much, David.
So Sarah or Amos, you can start.
Okay, good morning.
Good morning.
Am I audible enough?
Yes, you are.
Okay. So I'm going to share my screen right now. Okay, can you see my screen?
Yes, we can.
Okay.
Yes, we
perfect. Great. So I managed to run the model with the data set Dr. Helen shared with us yesterday. So I started by setting my working directorate. I went to sessions and set my working directorate, as you can see in my R console. So after that, I copied this and put it in my R script and run it again. Then after that, I loaded my libraries.
Sarah, please zoom in such that we're able to see your codes well.
Okay.
View, then zoom in.
Okay, doctor. Is that okay now?
Yes, thank you.
Okay, perfect. So I'm trying to load my libraries. So after I commanded R to read my data using the command read.csv. So I set an object, salaries. So if I run that, I can, if you can take a close look in my environment, my data is right there. So I had a structure view of the data. So when you run the summary, there are some variables that are read as characters. Yeah, so I commanded R to read them as factors. Okay, so if we run the structure again, you're able to see that they are now read as factors. Sex is a factor, discipline is a factor. So I went on, I started with the backward method. I used the lm command. So I commanded R to run that model. I named it model 1. As you can look at my environment, it's right there. So again, using the step command and setting the direction as backward, I was able to run that. So as you can see, if I go back a little bit, okay, right here. So if you look at my console, the first set given, or the first step, salary as a function of rank, discipline, yes, since PhD, like all the independent variables put in the model at once. So R gave me the AIC value. And also, you know, like Dr. mentioned yesterday, when you're using backward method, what R does is it keeps removing variable per variable, as you know, because the overall aim is getting a model that has the smallest AIC, that has the largest R squared, that has the smallest mean square error. Yeah, so R says if we remove 6, our AIC will reduce from 7965.19 to 7964.8. So if you go to step 2, now considering removal of the independent variable 6, the AIC value reduced to 7965.2. And if you look at what I've highlighted in my R console, now the model has changed, the function has changed. 6 is not there, it has been removed if you compare with this first one. Yeah, so like Dr. emphasized yesterday, none is it's like the stop sign. So after hitting that, no more variables are removed or added. So the final model, using the backward elimination method, I realized it was this: rank, discipline, years since PhD, salary as a function of rank, discipline, years since PhD, years in service. Yeah, so I extracted, okay, the AIC again, just to confirm. Then if you want, you can run the coefficient. I also ran the R squared value, adjusted R squared, it's this value here, and then the mean square error using this command here. To read this. As back AIC. That's why I adopted that here and not the entire model. So now that was the model I got using the backward, and those are the values that I got. The value of the mean square error, the adjusted R squared, and then the AIC value. Okay. So considering forward selection, I still ran it. Oh, sorry. Okay. Okay, sorry about that. Okay. So using the forward selection methods, again, the step argument or command, model 2, and then I set my direction as forward. So if I run that, okay, right here. So like Dr. emphasized yesterday, using the forward selection, the model starts with the intercept, and then other variables are added in, like so. Here R was telling us that if we add rank, our AIC would reduce from 8193.92 to 7998.9. So what it did, it went ahead and added rank, which is here, like you can see, and the AIC reduced to 7998.91 from this. So again, we went ahead and added discipline. Adding discipline reduced the AIC from 79966.2. As you can see here. Or what I forgot to mention earlier, I didn't set, okay, I can share that maybe later after I've run the stepwise selection. So after adding discipline, our AIC value is this, 7966.19. As you can see, this is a function. So we've hit the none code. We cannot add any more variables to the model. So the final model is this, salary as a function of rank and discipline. Okay, so okay, that is still extracting the AIC values. If you want, you can run the coefficients. Not found. That is because I didn't run this previous command. Sorry about that. I see not found. Okay, let's see where the error is coming from. Step 2 direction. Okay. data model 1 to model 2 direction. Okay. All right, so there it is. I've set my objects to that model. So you can get the coefficients as you can see there. I didn't set my reference level considering the rank category. So I took associate professor as the reference level. So its coefficient is the intercept here, which is 85705.87. And then this is the difference between the average salary of an associate professor and an assistant professor. Same here. This is the difference between rank professor and then associate professor. So we're running the mean square error. So the mean square error for this particular model using the forward method is this. Let's look at its R squared, adjusted R squared, error object not found. Okay. Oh, sorry, we were in backward. Apologies. I mean forward, sorry. Okay, right here. So running the R squared for the model using forward selection, it's this value here, the adjusted R squared. And then the mean square error is this. The AIC value is 7966.18, and then the CP is 4. So the final model that we got using the forward selection method is the one where salary is a function of rank and discipline. It's different from the first one we got using the backward elimination. Moving on to the stepwise selection, again using the command steps, I got my model. The direction here is both, like Dr. emphasized yesterday. So if you look into my R console, again, we started with a value of AIC as 8193.92. Then variable rank was added. And then the AIC value reduced to 7998.91. And then variable discipline was added, and our AIC value reduced from 7998 this to 7966.2. Okay, so after adding discipline, we realized that now we've hit the none code. We cannot add or remove any variables. Yes, so the final model I got using the stepwise selection is this. Okay, so running the AIC value using the stepwise selection method, I got it as 7966.186 and the CP as 4. And then the adjusted R squared was 0.4407437. And then the mean square error, I got it as 50790,667. So if I can stop sharing this and share my words that has a summary of the models right here. Okay, so the first model, can you see my screen? Hello, can you see my screen?
Yes, we can.
We can.
Okay, perfect. Thank you. So the first model came out as salary being a function of rank, discipline, years since PhD, and years in service. And the R squared was this. Residual mean square was this value. And then the CP was 7, and the AIC was 7964.75. Then considering model 2 using this was using the backward selection. Then model 2 was using the forward selection. The final model was salary being a function of rank and discipline. With those values, R squared was this, residual mean square as 70750, sorry, and then as the digits follow, the CP was 4, and then the AIC was 7,966. Model 3 using stepwise selection. The final model came out as salary being a function of rank and discipline. So considering these values, the best model I concluded with, given our data set, is this one, model 1, because it has the largest R squared if you compare with these two, and then it has the smallest AIC value if you compare it with these two again, and then has the smallest residual mean square, and also its CP value is 7. Doctor mentioned yesterday that the CP value has to be equal to the number of variables in the data set, and then you add a 1, which is the intercept. So when you do that, given the variables in our data set, you come up with 7. So I concluded with that as my model, that it was the best model. So I'm going to stop sharing this and go back to my R.
Sarah, thank you so much. I think that's enough. Just a small.
Okay, thank you.
A small comment, Professor Susan, then I proceed.
Okay, participants, after Sarah has gotten the final model, you still have to test the assumptions under multiple linear regression, which are normality of residuals, constant variance of residuals, independence of residuals. You also test to find out whether the independent variables are not correlated. You also find out whether there's linear relationship between the response and the independent variables. And at the same time, you have to look at the process you're looking at. For example, in that case, we are looking at salary. What really determines salary in the real nature? Yeah, in the real lifetime, what really determines salary? We have to go and read literature. So as you look at a final model, the computer gives you some model, but you have to look at the biological process behind the model and qualify the model. The other hand is that the simple model should be the best model, because then it limits how much money you're spending to collect data. Thank you so much.
Okay. Thank you so much, Sarah. That was so great. I think I've come to a conclusion when she used the different criterions to prove what things are basing on the data that affect that influence salary. So I guess all participants have been able to see the procedures moving step by step the way she was showing us. So that was a very good illustration. And in the conclusion, she said that according to the data that we have, basing on the largest R squared adjusted, and then the smallest mean square error and the smallest AIC. The first model was the one that was appropriate according to the data that we have. Thank you. And now I want to give a chance to the last participants now to take us through the chi-square, because Sarah has shown us how we can do a model building. And finally, we've come up with the model. Model 1 is the one that we are going to use in case we want to see what are the factors that influence salary. Like Professor Susan has mentioned, after getting the final model, all you need to do the normal regression. Now that you know the final model, then test for the assumptions and proceed on with the analysis. That is so great. Thank you. Let's move on to Amos to show us exercise 2. We are not going to go back to exercise 1 because it has been well shown.
Well, thank you, Doctor. Unfortunately, I didn't do that last number. I had also only done the first one like Sarah.
Sarah, have you done number 2, exercise 2? Is Sarah still there?
No, Sarah is no longer there.
Oh. Can you give her just rights again to share with us exercise 2, and then now we proceed, please?
Okay, let me move her. Yes, Sarah is rejoining back.
Okay.
Okay.
Let's have.
Thank you, Doctor, for the opportunity. I didn't do much with number 2, but I did something that I can share with my colleagues.
Okay, just share that and then now we proceed.
Okay.
I guess the rest of the participants, you're trying to mark yourselves on what you did, such that you get to know whether it was right or it wasn't right. Okay, the last exercise on categorical data, and then we move on.
Okay. Can you see my screen?
Yes, we can.
Okay, thank you. So, analysis of categorical data, I started with running the structure of the data like I did earlier and I shared with you. So I first of all summarized my salary variable to see the mean these descriptive statistics. So after that, I wanted, anyway, the reason as why I did that, I wanted to get a mean value from which I could set my salary as whether low or high. So those that were below the mean, I set it as low, and then those above the mean, I set it as high. Like you can see in that command that has, I told R to go to my data set salaries, get the variable salary, and then I use the if else command. Like you can see, I used my mean, the mean which was 11370 to set that. So after that, I ran using.
Trying to, Sarah, zoom out, zoom in. We can't. Some participants are not seeing the codes.
Okay.
Okay. Yeah. Fine. Continue. Increase the speed as well. Try to be a little fast.
Okay, sure. So using the my table command, I compared the salary. Now remember, it's categorized as high or low. So I looked at, I ran that salary and rank. So what I got, okay. The margin. Okay, margins.
Did you run the if?
Yes. Oh, no. Oh, I had forgotten here. Let me go back. Salary not found.
Just
Okay,
click at
so,
the end and then run.
okay, it's working now. So
Okay.
thank you, doctor. This was to categorize the salary as high or low. Then I compared it. Error, unexpected in salaries and rank.
Just click at the end anywhere and then you run that line again. You don't need to highlight it.
Okay, sure. Thank you, doctor. Okay, so now comparing those two, the salary and the rank, as you can see here, the 3 levels in our rank category, and then our salary. So I didn't do. Okay, if you want, you can run the margins and then the proportions. Then if you consider the chi-square, you see our p-value is less than the set level of significance. So there is a relationship or an association between the rank and the salary, and yeah. So like doctor, I said I didn't do much. I really didn't do much. Yeah.
Yeah, but Lisa, that's what I wanted to see. That is great. Thank you so much. Participant, it's always good, like in case we leave your assignments, you tend to try out on your own, because as you try out, you get well versed with the codes and things become easy for you. Whatever we are doing, by the end of the day, is what you're going to apply on your research. When it comes, for example, well, in case you want to do categorical analysis, you need to understand the principles. When do I do, for example, when do I use the chi-square and all that particular point, and also get to know how to interpret the results. So, Sarah?
Yes, doctor.
That has been great. Thank you so much. You can stop sharing.
Welcome, doctor. Thank you too.
Okay. Oh, yeah. Okay. Now let's move on. I'm going to be a little bit fast because there's a lot of information we have to cover. So I'm going to take a little time, maybe in 30 minutes. And when I because we divided time, Professor Susan has to come in to cover the remaining part. Now let's move on to people are talking about generalized linear models. Now, basically, I'm going to introduce logistic regression. But remember, the generalized linear models are very many. But let's start with the one that looks a little simpler compared to the rest. We've got logistic regression. Then you can also we can look at ordinal logistic regression, and then there's also multinomial. But for now, let's first look at one, and we proceed. Okay, because what is most important at the end of the day, you need to understand how do you interpret your data. And then Professor Susan has been emphasizing in this training, you have to attach the biological perspective. You've gotten the results, but when you go to the society, I mean, what do they really mean? It's the most important. So with the overview, we are going to just see some basics, the statistics we are going to use, and then interpretation of result. And then thereafter, I'll quickly go through R, and we see how do we run a logistic regression. When it comes to logistic regression, first of all, we need to understand the basics. Then they will enable us to understand quickly how to understand the results. I've already sent the PowerPoint. In case you don't have it, just type in the chat, then Prof will send you the material. For those of you who have not gotten, but I sent everything. We know that probability is the chance that something or an event will happen, and it always ranges from 0 to 1. Whereas the term odds, it implies that the probability that an event will occur, okay, divide by the probability that an event will not occur. We need to understand what an odd is, because it's a term that we're going to keep using. And even if when you read into literature, the way they interpret logistic regression, they use the word odds. All right, so the probability that an event occurring, you can call it y, and then the probability that an event will not occur, it's 1 minus y. So it's for those of you who have looked at sets, it's a complement. Okay, so that something will occur and then something will not occur. So those are the odds. For example, if a probability an event is 0.8, that is 80%, okay? Then the probability that event will not occur, you just get, we know that probability adds to 1 minus the event that will occur, then you get the opposite. So it is 0.5. So in that particular case, so the odds an event will be equal probability an event will occur divided by the probability the event will not occur. So which is now 0.8 over 2, and it gives us 4. So you can, for example, still you can say, if there is an 80% chance of rain one day, then there are 25% chance that it will not rain. So we've got odds of 80 to 20. And then somebody can conclude that maybe put it that it's 4 times more likely that it will rain than when it will stay sunny. Okay, now this is the definition I'm talking about when it comes to odds, all right? That is the probability of success over the probability of failure, probability of yes over the probability of no, okay? Having a success over the failure is what we call, so what you're seeing here in the definition is the odds of yes, okay? So my pi is the probability of success, then over the probability of failure. So still mathematically, you can make pi the subject, you can be able to get the probability of an event happening and the probability of an event not happening, whereby you can get the pi, and which will be equal to the odds over 1 plus the odds. Prof, noise. So let's proceed on. The event that has the highest odds is considered to be the favorite. And when the odds are low, then it means that the event is not likely to occur. I was just giving down here, for example, with the price data, the diamond data we are having, because remember we looked at, we finally categorized data into 2, the one of high and then the one of low. So now in that particular case, I say the odds of price uptake is the same as the probability the diamond price is high to the probability the diamond price is low. Okay, on the statistical tests, what we've covered throughout this particular training, it's important to note that actually whatever you're seeing on this slide, we covered it already. When I'm having my dependent variable here, and then I've got the independent variable. So sometimes, you know, as you're comparing, because remember we say that you have to look at the level of measurements. They're the ones that direct you on what kind of statistical test that you're going to use. For this particular case, in case your dependent variable is categorical in nature, and the option of a statistical test that you can use is a logistic regression or a chi-square test, which under your dependent variable is also a categorical variable. When it's continuous, your dependent variable is continuous and your independent variable is categorical. You can use an Anova to compare the means between the groups. Also, in case it is continuous in nature and also the independent is continuous, you can use a linear regression. And still, the moment your dependent variable is categorical, whether it's categorical, you can also run it against a continuous variable. That is what this slide is talking about. So let's move on, diving into logistic regression models. So you might need to ask yourself, why logistic regression models? We are saying that there's a lot of research whereby it has whereby the topics for which the independent variable is limited. Like the way we manipulated the data for the case of price and we created two variables, then it implies that you can analyze now that data using a logistic regression, because the point is that when it comes to logistic regression, your outcome or your response variable, your dependent variable is supposed to be binary, two. You're supposed to have only two outputs. So that's why sometimes I call it binary logistic regression. And this particular type, it's coded as a dummy variable, as 0 or 1, okay? Did not vote or voted. Okay, and now on this particular slide, I'm giving more examples. Sorry. Okay, the examples that we are having here, for example, whether or not a person smokes, it's also an example of that you can apply in logistic regression. One smokes, one doesn't smoke. And also another example is success of a medical treatment. You can be testing a certain treatment and then you've got two outcomes. Either a patient survives or a patient dies, depending on the treatment that you're adjusting. So it's important to note that when we get to ordinary regression, the model predicts the mean of y, or the mean of the dependent variable in combination to other predictors. Whereas when we come to logistic regression, we are looking at the mean for the case of in form of a success, whereby we get the numbers of the successes in that particular case, in case we are considering yes or no. So the yes will be on the top, that is the proportion of success, then divide by the total number of trials, that is adding the yes and the no. So in the end, we are coming up with the proportion of success. So the logistic regression helps us to predict the true proportion of success pi at any value of the predictor. Okay, I'm not going to go into the mathematical bit, but at least I'm just going to share with you what exactly that you expect to see in case we are looking at a logistic regression. Our response, the y variable, it's supposed to have a binary response, like the example that we looked at. And then the dependent variable the independent variables can either be categorical or they can be continuous. It doesn't matter. But the point is that your y has to be a binary response. And then at the end of the day, you need to keep at the back of your mind that what proportion of success are you measuring in relation to the independent variables. So when you look on my slide, remember, I'm looking at the probability. There are two things involved, the one of success and then the one of failure. So when you check in various textbooks, you will see that in a logit form, we always have a pi, the probability of success over the probability of failure. And then we put a natural log, some people call it in. And we are looking, for us to, we are linking what you're seeing on this right-hand side. It is a link. We are moving now from a linear regression. There is a link between a linear regression and then a logistic regression. That's why you're seeing that at the right-hand side of this equation, what you're seeing, you're having beta naught and then beta 1x. So which is what we saw earlier in a linear regression model. But now for logit regression, now instead of having y here, which was for the case of a linear regression, now we put it in terms of odds because our outcome, it's binary in nature. And then from here, you can take the log, you can take an exponential such that you're able, when you put e on this side and then e on the other side, you are able to create pi as the subject or the probability of success, and you'll come up with this particular form. In case you're interested in the math behind, you can do it on your own, but let's understand the basics. This is what I've just talked about. But then when you look at this particular form, we only have one independent variable. So the point is you can have as many independent variables as you can. It doesn't matter. Like I said, the moment it's only one independent variable, then that is a simple logistic regression. more independent variables, then we'll come up with a multiple logistic regression. What you're seeing on the right-hand side, which is a log pi over 1 minus pi, that is a link function that permits you're linking to a linear regression. But in this particular case, our left-hand side for it is written as a log form. Okay, so this one, you can just, you can keep adding as many variables as you can, so it doesn't matter. Most of the time as you read, you'll find that when you're looking at logistic regression, it is in form of an S-shaped, and you're seeing that you're running from minus to negative, from minus infinity to positive infinity. So for it, it's in the form of an S-shaped curve, and whatever that you're seeing on our Y, the S is the one that depicts my Y outcomes, the zeros and the ones. Okay, I've mentioned about how it looks like, its particular form. It assumes a linear relationship between the predictors and the log odds. Kindly look at it here clearly. What we are having this side, it's linear. It's a linear. You're putting a linear relationship, beta naught plus beta 1x, and then this other side, what we are having, we call it log odds. Pi, the probability of success over the probability of failure, is what we call odds. Now, to read it together, it is called log odds. So that is why they're saying that it's a relationship. It assumes a linear relationship between the predictors. The predictors are my independent variables in relationship to the log odds. All right. Now, that I've talked about that. So why it's always the common way why we go on to use the logistic regression most of the time is that we want to compare two groups and see how do they look like when you consider the ratios in the different groups, as we are going to see in the different examples. Remember, we saw what an odd is. Okay, when you're looking at the probability of success and then the probability of failure. So that is an odd for one group, but you can also have an odd for another group having the same story. So for you to get the odds ratio, it means that you have to get the odds of one group, you divide by the odds of the second group. That is from odds, and then when you say odds ratio, you're trying to compare two groups. Okay, and we are going to see it in R practically. When an odds ratio is greater than 1, then that one indicates that the condition or the event is more likely to occur in the first group. And if the odds ratio gives you less than 1, it indicates that the condition in group 1 is less likely to happen. So this is going to support us as we are interpreting the results. Okay, now when we come to this particular slide, remember everything emanates from probabilities. And we said earlier that probability is one of the... Okay. Okay, let me type in the chat. Yes, Anthony is saying that I'm too fast. Are we on the same page on what I've explained so far? Hello? Okay, fine. Sure, let's proceed. I'm very fast. I'm going to try to be moderate. Okay, we've got probability. Everything starts from probability. Then after probability, we move on to odds and then log odds. We know that the probability of success is equal to its mean, which in this particular case, it's mu. And we say that when you come to the odds, okay, you have the probability of success over the probability of failure. So in terms of odds, my numerator is going to be the success, which is mu, and then the opposite, the 1 minus mu, will be my failure, okay, the probability that something will not happen. So it will give me an odd. And then from this odd, I can get log odds by just putting the log odds over what I'm having here. You can still write it as the probability of success. the success, call it you can say maybe the probability that the price will be high. If that's what we are looking at, the price of diamond will be high, and I call it y is equal to 1. So it will be the probability that price will be high over the probability that price will be low. Y is equal to 1, then over probability that y will be equal to 0. And then you can also take the log odds. So we'll see how the mathematical part comes in. However, when you look at probabilities, we say that they lie between 0 and 1. However, when you move on to log odds, it implies that you're opening, instead of looking at a range between 0 and 1, now you can run from minus infinity to infinity. For example, in case you get your mu to be equal to 1, we want to look at the odds here. When you put 1 and then 1 minus 1, in this particular case, you come up with an infinity, and the log of infinity is equal to infinity. When you take your success to be, the mu to be equal to 0.5, when I'm just putting everything on what I'm having here, I'll get a 1, and then the log odd of 1, the log of the odds of 1 is 0. And then in case it is 0, then it will open me up to go to minus infinity. The point is that what logistic regression does, it gives us an opportunity when you're transforming the probabilities from 0 to 1, and then opens it up from minus infinity to infinity, the one that is unbounded, implying that our log odds can lie anywhere from minus infinity to infinity. Okay, here I was just giving a simple example. Remember how an equation looks like. What you have to note at the back of your mind is that what changed here is my response, the way I define my response variable, which is a log over the probability of success over the probability of failure. That is mu over 1 minus mu. But this other side, on the right-hand side, it still shows the relationship with the independent variables. For example, here I considered the beta naught plus beta 1 gen. This was gender. So it implies that in this case, I had gender, which was a 0 and 1, okay? It was a dummy variable, 0 and 1. And we said that when it comes to logistic regression, it doesn't matter. You can run it against categorical variables or continuous variables. And I said in case I put my gen, for the case of female, in case I put in 0, then it implies that the log odds, my intercept, will be equal my intercept will be equal to the log odds. Okay, that is what I'm having here. And in case my gen is equal to 1, if I consider it to be the females, it implies that now my log odds will be equal to beta naught plus beta 1. But remember, all these parameters are defined by the model, so we shouldn't get scared. But try to transfer what I'm explaining to what we did in linear regression. My tables are not coming up. Okay, let me just proceed. There's my slide had an example, but let me just continue. We'll do it because it was just an example that I thought that will support us. When we move on to R, as we're going to use on the data set that I sent, we use a function GLM. And then remember in linear, we used LM, but this time around it is GLM. It's logistic regressions falls under general linear models. So in this data set, for them, they are considering gender, then versus height. And what we're going to see in the hop command, if you're looking at logistic regression, what do we exactly do? So in this particular case, there is another argument called family. So we use the family to be equal to the binomial, because remember with the logistic regression, there are two outcomes, a yes or no, depending on what you're looking at. And then still within the command, we'll indicate which data we're considering. So data will be equal to our data set. And then also, like in LM, we ask for a summary, and then we are able to interpret the result. Somehow the output looks the same, but in this particular case, yes, it shows you the equation that yes, it's a GLM. Your formula, you considered in this case gender as your independent variable. Remember, gender has 0 and 1, and then it was looked at against the height. all right? And then family binomial, it gives you the divergency residues. Remember what we talked about residues, that it gives you a summary plot, and they support you when you're measuring a mode of best fit. We also further go on to get the estimates, the standard error, the Z value, and then the P values. But now we're going to understand how do we interpret them. In this particular case, before we get to R, I get an estimate for height, the estimate for the intercept, basing on my model. Remember, what is different here is how I coded my response variable. I've got the standard error and then my p-values, okay? Testing it against the hypothesis that my alpha is equal to 0.05. So we want to see, again, when we test, do we reject the null hypothesis, or we fail to reject? So where you're seeing the red circle, those are the estimates we are being given. That is the same thing, but now from here, when you look at the model we had, how the equation is written like, you are able still to calculate the probability of, for example, in this particular case, that of height, okay, of somebody looking at gender, and maybe you calculate the probability for height, because our pi is the probability. Having gotten, because you first start getting with the odds ratios, and then after getting the odds ratio, you're able to move on to the calculating the respective probabilities. So here they're saying a proportion of females at that HGT is the height. This data is just an example. We're going to do everything in R and then see. That is the same example. Maybe on this slide, the take-home message is that the moment you get the estimates, you can convert the estimates into odds ratio. How do you do that in R? By taking the exponent of the estimate. That is very important. Having gotten the estimate of a given group or a given independent variable, for you to get the odds ratio, because most of the papers in publications, when you're reporting your results, they report odds ratio. They are easy to interpret, and you can quickly use them to make conclusions or recommendations. And so from your estimate, the moment you take the exponent of the estimate, it gives you the odds ratio, depending on what you're looking at, whether it's a categorical or it's a continuous variable. Okay, and also it's important that you look at your p-values such that you test the hypothesis that you put across. Okay, it's always important to note that like a single binary predictor for a binary response, what we've looked at, we've looked at a binary variable whereby you've got the success rate and then the failure rate. And then the predictor variables can also be in form of groups. So what we looked at earlier, there are various methods that you can use, especially when your dependent variable is grouped. For example, maybe it has got two outcomes. We saw the chi-square test for a two-way table. What we learned yesterday and what Sarah has presented. In that particular case, still we saw that our dependent variable was binary. Still, you can do a Z test, or you can compare two proportions. And I'm glad to say that all the things have been covered in our training. And then now the last method, which is the binary logistic regression, we are going to use it. You can use all these particular methods interchangeably, but you have to know what the right statistics that you're supposed to apply. Okay, now I created a simple hypothetical example that is going to support us to understand how do we explain the variables. Let's go through slowly by slowly, and then we get to know how we're going to explain this the moment we move to R, because the moment you understand the explanation, all the values that what we are going to run in R is going to be simple. I used a hypothetical example, which was it was a research that was done among the uptake of e-commerce among students. Actually, this study was conducted at Makerere University. We are looking at the uptake of e-commerce among Makerere University students. I'll not talk about the details, but I'm just giving you just a little background. And the variable uptake, okay, e-commerce uptake had a no and a yes. And then we are looking at it in relation to gender. We saw how we create these tables using having a contingency table in chi-square, whereby you're able to get the frequencies or the different proportions according to category. Okay, we had a no and then a yes. We had two groups. Okay, my response was e-commerce uptake, which had no and then a yes, and I was looking at it in terms of gender because we wanted to look at what are female Makerere University students more likely to take up e-commerce compared to males. Remember, we are comparing two groups, and now the probability of success. The probability of success is that the probability of e-commerce uptake. Okay, that we are going to look at. Still, the outcome was binary in nature, no or yes. So what happened from this previous slide, we've got the females who said no to e-commerce uptake were 47, those of yes were 46. And then the males were 53 that said no to e-commerce uptake, and then 54 said they were taking up e-commerce. So looking at these two groups, we want to compare, and then we move on into R. So in case I want to get the odds for females, remember what we said, the odds for females, I'm looking at two groups. I've got the female and then the male. The odds for e-commerce uptake, the odds for e-commerce uptake among female students, it is going to be yes over no. That is 46 divided by 47. And now the odds of males taking up e-commerce, it's going to be yes over no. Probability of success over probability of failure, which is going to be 54 over 53. Now, those are the odds. I've got the odds for female, I've got the odds for males. Now, for me to move on to the odds ratio, I'm going to get, now, I'm going to divide the odds for female divided by the odds for males. That is, it will give me the odds ratio. Okay, let me pause a while and go in the chat and ask, is it okay? Let me go to the data set. Are you following me? What I'm talking about? Okay, great. Fine. Let's proceed on then, such that we quickly get on to R. All right, now let's move on. Kindly master how we're going to interpret. This is what I've been talking about. How are we going to get the odds ratio, the ORs, because they're the ones that you're going to report in your publications. You get the odds of uptake of e-commerce among one group, and then divide by the odds of uptake of e-commerce among the other group. Here we've got the males and the females. We've just talked about the odds for uptake of e-commerce with the female group. It was 46 over 47, yes over no. Then for the males, yes over no. And the OR that we are getting is 0.961. Okay, now what is the interpretation? Remember what we said. And when you look at our previous result, the OR is less than 1. So how do we interpret that? We say that the odds of uptake of e-commerce among the first group, those are the female students, are 0.96 times, okay, times the odds of uptake of e-commerce among female students. We are comparing odds for so the ones of female, you can say, we've got various interpretations. The first one is that the odds of uptake of e-commerce among female students are 0.96 times the odds, okay? It's a ratio we are looking. So you can conclude like that. Somebody else can have a different interpretation, but they all get to the same interpretation. So you can also have interpretation too, whereby you can say, because you can say the odds of uptake of e-commerce among female students is 3.9%. How do you get that? You get the odds that you have previously, and then you minus it by 1 and you multiply by 100. However, interpretation 3 is the one that might look maybe very easy for you, which says that female students are 0.96 times less likely, okay? There is a concept of being more likely and then less likely. I guess you've encountered these words when you're reading certain publications, that the female, the group that we are comparing with, our top group is female, that it is 0.961 less likely to take up e-commerce compared to the male students. So those interpretations, you can adjust them to anything. With a variable being significant, it's the same thing that we've been talking about. Then like logistic regressions have got coefficients, okay, that we need to interpret. We mentioned them already, the beta naught and the beta ones. The moment, if you're considering that the intercept, having all the other independent variable equal to 0. So that will give you, for example, in the model that we talked about, the one of the hypothetical one, if you put your gender equal to 0, the 0 was for the case of the males. So it was giving us the log odds of uptake of e-commerce among the male students. And then the moment we put 1, we ended up with beta naught plus beta 1. So for it will be the log odds for the uptake of e-commerce among what? Among the female students. And then our slope, the beta 1, will give us the difference between the two. The log odds of uptake of e-commerce among the female students and okay, yeah, that is what I've just mentioned. I'm going to go to R such that we see how do we push on. Let me pause and get the questions. Day 6 material, please. Prof is going to do that. Day 6 materials. Kindly check in the chat. Professor Susan is sending the materials in case you missed, but all the materials were sent. Okay, let me ask in the chat, have you gotten the feel of what logistic regression is all about and when we are supposed to use logistic regression, such that we move on to R? Okay, a little bit. What does the odds of 0.6 mean? Okay, let me now go slow on what odds are. I started with the basics, and I said that for you to understand logistic regression, it is always good to understand the concept of what an odd is, because it is the word that we're going to keep using all the time. Okay, and we started with asking ourselves, what is a probability? Okay, and we know that with a probability, it is a chance that an event is likely to happen. Okay, and then when we get to odds, we are comparing two things. All right, you're comparing the probability that something will happen over the probability that something will not happen. For example, I would say that when you have, because we said that logistic regression, it looks at the outcome when the outcome has got two levels. For example, we said a yes or no. When you're looking at another example, you can look at for a case of odds where it will rain or it will not rain. You get one category and then compare it with the opposite. All right, whether the medicine will work successfully, that is the success, or it will not work successfully, that is the what? The failure. So you're looking at the success is always on the top, and then the failure is always in the denominator. That is an odd, comparing something that will happen over the probability that something will not happen. Only. So is that okay? Look at a scenario whereby your dependent variable has got only two categories, high, then low, true, false, yes, no, smoking, no smoking, all those ones. All those scenarios can be used in logistic regression. Even you can consider sex as your, because it has got a male or female. Male can be yes, female can be no. You can also run your gender as a logistic regression. So can I proceed to R? Somebody is saying that suppose you have 3. In case you've got 3 categorical, in case your dependent variable has got three levels or 3 categories, it implies that in that case, logistic regression will not work. You'll either go into ordinal logistic regression, whereby there is an order, or multinomial logistic regression. But for the case of binary logistic, always your outcome should have 2 levels, a yes or no. More than 4, you move on to multinomial. It is a different, statistical test that you use. 2 levels, it's a must. Dennis, yes, it is a must. There's supposed to be 2 levels for you to use logistic regression. If it's more than that, then you either move on to ordinal or you do multinomial. That's why it is important to understand the kind of data that you have. It will support you to use the right statistical test. Okay, I'm stopping to share, then we go on to R. Prof is telling me I have only a few minutes, so I need to, okay, now, Prof, you need to first come. I'm moving on to R. Just go to R. The 6. That's it. Okay, now we are, okay, now we've moved on to R. We are going to use the data set that is called my data. Let me hope you have it. The my data set that I sent, and we are going to be running the logistic R script. Kindly now let's get to our computers and then open the logistic R script, and we're going to be using my data set. You don't need to report any marginal. They said no. Oh, that is something different. Yes, you can report them, but for now we are starting with the basics. Of course, like I'm giving you an introduction, and then the marginal effects can come in later. But let's first understand how because you keep adding from what you have, then you can go ahead and add in the marginal effects. But let's first get the basics first. So let's get on to R. Load your R scripts and also import your data into R and load your my data script. Looking at the my data set that I sent you, it has got 4 variables. It has the GRE, that is the graduate record exam score. It has the GPA, the grade point average. It has the admit, that is admission into graduate school, which is binary. It's either you're admitted or not admitted. And then the one of rank, it represents the prestige of the undergrad institute that somebody went to. So the research question was that a researcher wanted to find out how these different variables, okay, affect someone's admission into a graduate school. So I'm going to load my libraries. We are running the logistic R script. Let me check in the chat. Are we on the same page? Kindly send a link to me. I joined using link. Okay, Rachel is saying that we're on the same page, plus Samuel and Okay, let's go on. Now let's load, because what I know right now, we can all load the libraries, which is a very big achievement. We need to load our libraries. Go to your Logis RF. Okay, we are installing the cart library. Please go on. It will run and then later you load it. Okay, now after loading our libraries, we need to import the data. Please, is it necessary to order the packages? It is not necessary. The point is having the right packages. Whether you load them, the first one, the other one is the last, there is no issue with that. Now what I do, I'm importing my data into R, okay? Please do the same. So now I named my data SCSV, I called it graduate, okay? That is an object. Remember we said you can call it any name. I also wanted to say briefly on how my data looks like, taking the first 6 columns, sorry, the first 6 rows. I'm saying I've got admit, the GRE, the GPA, and then the rank. I've just, remember, I also sent the description of these variables. I repeat again, admit is admission, which is a binary variable, yes or no. The GRE, that is the grade record exam, okay? And then the GPA, that is the grade point average, because all these things are considered when somebody is being admitted in a graduate school. So as a researcher, we want to find out. This data set, I picked it from R. Like I told you, in case you want to practice, R has got already embedded data set that can support you as you're practicing. So it's where I picked it from. Now let's move on. I wanted to see the structure of the data set. I guess you can all run that, and they tell us that admit, now R is seeing admit as an integer, then GRE as an integer, GP as a numerical, and then rank as an integer. But remember, we need to tell R that no, look at admit and rank as factors. So I'm going to run these lines. I know you already know how to do that. And then I also move on. I check my structure again. I say like, yes, right now it is what I want. I can get the summary in case I'm interested to do descriptive statistics a little bit. I run that, and then still R shows me that, okay, when I do my summary statistics, I'm able to see the admit, the 0 is 273, and then 1 is 127, the GR, because they are continuous, and then the rankings that I have, all right? Rank 1, 2, 3. One shows, it's looking at the prestige of an undergraduate institution that you went to. So 1 ranks the highest, then 2, 3, and 4 the lowest. Okay. In case I want to, my admit is my dependent variable, all right, which is a yes or no, and then rank has got 4 variables. In case I want to see how in a contingency table, how these cells are, I do table, then I run that, okay? I've put my graduate admit from my graduate data set. I pick the admission, and then also from my data set, I pick the rank from table. Remember, table just gives us frequencies or counts. And it is telling me that from the previous, those who were not admitted under 0, from the prestige institution number 1, there are 28, then in 2, there are 97, and so on. Then those who are admitted from number 1, there are 33, from 2, there are 54, and so on. However, in case you don't want to use this command, you can also run the one of X tabs, and then it is going to give you the same thing. If I run that, it will be very clear and tells me, okay, this side I've got admit, and then on my columns are the ranks. They're just giving us the frequencies, all right? Kindly reshare the My Data CV. Prof, please. Okay, it has been sent. And now, having seen that, you know that always when you get the data, why do I need to convert admit, rank as factors? Wow. Okay, that's an interesting question. Now I'm going to move on. on how to run when you're running a logistic model. David is saying that I'm quite fast. Prof is on my neck that my time is up. Okay, let me type in the chat. Could you do a quick recap? Okay, no problem. Let me do a quick recap such that we're on the same page. Having known that our dependent variable is binary. Binary meaning it has got two outcomes, a yes or no. In this case, with the data set that we are going to use, it has got two outcomes. Either person is admitted or the person is not admitted. Okay, so I think you're seeing where the odds are. The odds of a student being admitted, the probability of somebody being admitted, that is the probability of success over the probability that somebody is not admitted. Prof, that you took my time last time, so you also give me more time. Okay, let's continue. Now, somebody was asking why we are converting, why we're using as factor. Remember, R will not understand whether you're considering a certain variable as category, whether it's in category form. So for you to put to convert it into a category, you need to use as a factor. Okay, I'm going to proceed. Good enough, we are going to share the recordings. And I said that using this command xtabs, and then my data, I named it graduate. It's an object that I'm using. That when I'm going to use graduate. Yes, logistic regression is very important because it's commonly used in all the models. So xtabs, a small admit plus rank. So when you look in my R console, I'm able to see the frequencies, the number of those that are not admitted, and then the number of those that are admitted in the 4 different institutions, the one that I've considered the best in the country, from 1, 2, 3 to 4. We are given those that are not admitted. For example, we are having 28. They are not admitted in the first institution 1, 97. They're also not admitted in 2, and then 35 in 55 in 4. And then those that were admitted in 1, they were 33, and so on. Okay, they just gave us a feel on how our data looks like. Now let's go and run a logistic regression such that we get to know, okay, how do you interpret the odds in case you're doing your research and your outcome has got your outcome variable is binary in nature. How do you do it? Okay, when it comes to logistic regression, remember we said it is one of the GLM models. So we use a GLM command. Remember we said R has got an inbuilt function. You can type in help, and then you can type help GLM, and then R will give you more illustrations on how you can go ahead and interpret the result. So GLM, remember initially with the LM, with the linear models, it was LM, then we put in the dependent variable, then as a function of other variables. Now in this particular case, instead of LM, I put GLM. Okay, when you look at what I'm showing, even R supports you to understand what exactly do you want to do with the GRM. You need to state the formula, you need to state the family of where the kind of regression that you're going to do, among other methods. So I type admit as my dependent variable. Remember, it's binary now. Okay, and then I want it to, my admission is a function of, I've considered GRE and then GPA plus rank. Maybe also to note that, please zoom out. Note that you can also do model building with the GLM models, such that it gives you the right, am I doing the right thing? Prof, I'm supposed to zoom in, zoom out. Okay, I'm zooming in. Hope that, okay, hope that is clear. So among, like I said, you can even do model building such that by the time you do your fine analysis, you're using the right model that clearly fits your data very well. So I picked the GRE, the GPA, and then the rank. Remember, now the first, this is my equation, okay, my formula, the one that I'm putting. Then the next argument that I need to put is data. My data is called graduate. Something very important that was not in LM was the family, because I'm considering my outcome to be binary. So the family I'll consider is binomial, by from 2, binomial, yes or no. So with the logistic regression, we will be indicating the family as binomial, but this family will vary because when you go to ordinal logistic and then you go to multinomial, it might be different. So you need also to master that. So what I'm going to do, I labeled it my logit. All right, the object that I named it, you can give it any name. So what I'm going to do, I'm going to run that particular line. The moment I run it, and then I need to see the result. So I move on to the summary, summary of my model. Now let's go through the summary and see. Okay, what we are having, still in the summary, it first tells you that yes, it's a GLM. You've got admit and your family, the family is binomial and so on. It gives you your residues, the divergence in the residues. Remember, the more we keep the model that gives us the smallest residues, they're the ones that supposed us to give us the model that clearly fits our data very well. Now let's move on. This is the output that we are getting, the coefficients. And within our coefficients, we've got the estimate, the data, what the data is estimating. We've got an intercept, the estimate for the GRE, the GPA, and then we've got the standard error, we've got the Z value, or you can call it, also called the world Z test, and then the PR, our probabilities. So we need to get to know, how do we interpret the results? Remember, with the linear regression, my Y was just a value, okay, that a unit increase in this causes a change in the Y variable. But keep at the back of your mind that this time around, your Y variable is read as it's read as the log odds, okay, over the log odds of whatever that is inside the success that you're talking about. Okay, now I'm going to take the first one and then we go through. For example, in case we are looking at the GRE, we are given the estimate as 0. Really? Okay, I'm only going to explain this a little bit, then I hand over. My GR is, the estimate I'm having is 0.0022. So that one I would say that for every unit change in the GR, so the log odds of admission, okay, versus non-admission increases by 0.002, all right? And then the same will happen to the GPA, that for every unit change in the GPA, the log odds, remember the emphasis of being admitted to a graduate school, will increase by 0.80. I'm looking at now, I'm interpreting my right-hand side by indicating the log odds. And then when I move on to rank, in the ranks, my reference will be reference 1 in relation to the very prestigious institution. So having attended a graduate institution with rank 2, with a rank of 2 versus an institution with a rank of 1 changes the odds ratio by minus 0.675. Okay, but sometimes it's pretty hard to to interpret out using the estimates. Most of the publications emphasize that you write log odds. You interpret the results in terms of log odds. So I'm going to go there briefly, and then kindly you get a recap from the recording, because there's more information that you need to get from Professor Susan. You can get the confidence interval like the way we did before, and then we continue. Now I said, in case you want to get odds ratio only, what you do, you take an expo of the coefficients. This is what this command tells you, that an expo inside the coefficients of my model. Okay, when I type that, I run it. So they have given me the coefficients for the GRE, the coefficients for the GPA, and then the rank. So here you can say, for example, in case I'm going to consider 0.50, in this particular case, my odds ratio, what is up is rank 2, I'm comparing it to rank 1. So, and I've got a 0.50, which is less than 0.0, which is less than 1. So I would write and say that I would conclude and say that when the odds ratio, a student to be admitted, okay, in an institution, the rank of being admitted in rank 2 is 0.5, less like somebody is less like 0.51 times less likely to be admitted in rank 1. And the same applies to the rest, because you're interpreting it in relation to rank 1. You come to rank 3, you interpret it in terms of rank 1. So in this particular case, it will be 0.2 times less likely, the one in rank 3, to be admitted in rank 1. Okay, you can follow through the other codes in case you want to get the confidence interval for the coefficients. So I'm going to stop here, such that I hand over to Professor Susan. We can keep it, we can still get more details, but basically that is what logistic regression is all about. Thank you. We'll send more the recording such that you're able to follow.
Okay. Okay, good afternoon. Good afternoon. Can you hear me?
Yes.
Okay, thank you. Let me share the material we are going to look at today, our last day. We will look at factorial treatment structure, we'll look at split plot design and repeated measurement. And I'll first of all look at simple theory, then we'll go into practical. So we'll look at factorial and split plot, look at the practical, then come back to repeated measurement so that we don't lose the theory. Okay, in a factorial treatment structure, we have what we call a factor. A factor is a treatment variable which is varied at the will and under the control of the experimenter. Okay, a factor can be quantitative or qualitative. For example, quantitative variables, we can have levels of a fertilizer in grams or kilograms, depending on what you're investigating. Qualitative variables, we can have types of fertilizer. For example, nitrogen-based fertilizers, phosphorus fertilizers, etc. The particular value which a fertilizer takes is called the level of that factor. For example, we can have nitrogen, but with levels like 0.2, 0.5, 1, 10 grams, 15 grams. So those quantitative values represent the level of that particular factor. In a factorial treatment structure, each experiment receives one level of each factor. A combination of the factor level makes up a treatment combination. So if you have nitrogen-based fertilizers and phosphorus fertilizers at 2 levels each, then you're going to end up with 2 by 2 factorial treatment structure, and the number of treatment combinations is going to be 2 times 2, making 4 treatment combinations. And when we are doing replication, we replicate at the treatment combination. So in each plot, you will apply the nitrogen and also phosphorus at the same time, so that the main aim of factorial treatment structure is to investigate the interaction. So the form of expressing factorial structure is 2 to the power n, where 2 denotes levels and n denotes factors. For example, 2 to the power 3 represents 3 factors, say nitrogen, phosphorus, potassium, each at 2 levels. And 2 to the power 3 gives you 8 treatment combinations, which can be replicated r times and applied to a design structure of your choice. Now, some people say factorial treatment design. The factorial treatment is not a design, it is a structure, the way the treatments have been randomized to the experimental units. You can have a factorial treatment structure in a CRD design. So if you're writing your proposal, you would say that you have a CRD design with a factorial treatment structure of 2 by 2, and then you indicate the factors and the levels. So that would be the right way of reporting your design. It can be a randomized complete block design with a factorial treatment structure. Advantages of factorial treatment structures: we are able to investigate so many questions simultaneously with the same amount of labor or even less. So we have increased precision because we are looking at interactions between factors, And we are also looking at the main effects. So if we have nitrogen-based fertilizers and phosphorus fertilizers, we will look at the effect of nitrogen, the effect of phosphorus, as well as the effect of the interaction between phosphorus and nitrogen. Unlike in a single design where we just look at the effect of nitrogen only. Okay, so that is the advantage of having a factorial treatment structure. Interaction comparison investigates whether the effect of one factor is the same at different levels of the other factor. So when you perform an analysis of the factorial treatment structure, if the interaction is significant, then clearly the effect of one factor is different at the different levels of the other factor. So if you have a significant interaction, then you don't need to go and interpret the main effects, because all the information you want about the main effects is within the interaction. However, if the interaction is non-significant, then you can look at the main effect independently. You look at the effect of nitrogen on yield, the effect of phosphorus on yield. Okay, so some scientists, when they see that the interaction is significant, the main effects are significant, he will go ahead and interpret the main effects, then you also look at the interaction. So it is best you look at the interaction. It gives you all the information you need about the main effects and also the interaction. So this is a Anova table for a factorial treatment structure. We have factors A and B at small a levels and small b levels, conducted in a complete randomized design. How do I know? There are no blocks indicated, so I assume that is a complete randomized design. So the source of variation in that case would be the main effect of A, main effect of B, the interaction, the error or experimental error or residual or unexplained variation, and the total. Treatment A will have degrees of freedom, the number of levels -1. Treatment B will have number of levels for B -1. The interaction will be these two multiplied together, and the error would be AB into the number of replicates -1. The total is N -1. We have sums of squares. There are formulas you can look up in literature for these formulas if you're interested. The mean square is the ratio of sums of squares divided by the degrees of freedom. So for each row, the mean square for that particular row is the sums of squares divided by the degrees of freedom. So we go on to the ratio. The F ratio is the mean square divided by the error mean square. So we are able to get the F ratio, and if you're conducting an analysis, you get the corresponding p-value. Okay. So that's it about the factorial treatment structure. When we look at the practical, we'll be able to see that if you come up with a significant interaction, then you will draw what we call interaction plots. If the interaction is not significant, then you don't need to construct the interaction plots. We look at the main effects, and what you do your treatment comparisons, whatever method you can use. You can use LSD, you can use contrast if you have pre-planned comparisons. If you do not have pre-planned comparisons, then you do not need to use contrast. Remember, those are questions that you plan at your proposal stage. Okay. We have what we call split plot designs. In most cases we have, especially in agroforestry experiments or some agriculture experiments, we have factors that require large plots, while others require small plots. So in that case, factors which require large plots end up taking the main plot, and then we split the main plot into smaller plots called subplots, where we randomly apply our other factors which require smaller plots. For example, trees require large plots while crops can be grown in small plots. The other example is when we do an irrigation experiment, irrigation requires large area. Otherwise, if you have small areas for irrigation, there will be what we call crossover effect. The irrigation levels from one small plot will end up in the other plot, so you will have confusion in your results. That's why you see irrigation takes up larger plots, and fertilizers can be applied on small areas within particular irrigation treatments. This is an example of a split plot design. You can see that the big box here, where I'm moving my cursor, where there's rep 1, is a block, and the strip, the vertical strip, where you have N2, N3 is the main plot. The main plot is subdivided into smaller plots where we are applying V1, V3, V5, V2 up to V4. So within those small square plots, those are the subplots where we are applying our varieties. The main plot, we are applying nitrogen. Okay, so if you want to look at this experiment, you can go to this reference book, and it is a book where they use R for experimental design, so you can easily actually refer to it if you want to do any analysis in experimental design. So whatever we don't cover, please refer to that book, or you can actually Google and get a lot of material about R for experimental design. There are a lot of YouTube videos that you can actually listen to and improve your skills. So here, this is also an elaborate design. You can see that the main plot, this is a block, complete block. And within a block, we have 2 main plots. And in the 2 main plots, each main plot, we subdivide into 2, making the subplots, these ones with these small arrows. They are called subplots. So we have Anova table here representing the split plot. In a split plot, we have 2 types of error because we have variation at the main plot and then variation at the split plot error. Split plot level. Now, when you're writing your code in R for split plot analysis, you have to specify the whole plot error, and whatever remains now goes to the subplot error. Otherwise, if you don't specify, you're going to get an analysis of variance like for a factorial design. So the model here, you see that we have the overall mean. If you can see mu is the overall mean. Yijkl is the response. And then we have the block effect, which has a subscript k. We have the factor applied to the whole plot, which has a subscript I. And then we have the error at the whole plot level, which has subscript ik, k for the block, and I for the factor for the whole plot. Then for the subplot factor, we have beta, j, it is the subplot factor. Then we have the interaction, ij, the interaction between the whole plot factor and the subplot factor. Then the error at the subplot factor, epsilon ijk. Now, when you are in R, you must make sure you specify your whole plot error factor very well. That means you need to know the degrees of freedom, okay? So we find that the number of blocks here are 2. We end up with 1 degree of freedom for block. We have 2 factors, 2 levels of factor A. We end up with 1 degree of freedom. Then we have a whole plot error, which is 1, because 1 times 1 is 1. So there was no replication here. And in that case, you won't be able to test any effect of factor A And then we have factor B with also 1 level, I mean 2 levels minus 1 gives you 1 level. The interaction ends up to be 1, and the subplot error is 2, and the overall observational error is 8. So if you add up this 1, 2, 3, 4, 5, 6 plus 2 gives you 8. So you see that the importance of replication comes in here in testing your factors. If we don't replicate, if we had done this in R, it would tell you that it would give you none for the estimates of the p-values. It can't estimate them because we have not replicated. So I have also included a dummy Anova showing you the source of variation, the factors for main plot and subplot, error A, and then error B, the sums of squares, the mean square, and the F ratio. Okay, so we are going to, we've also find that the split plot involves assigning levels of factor A to the main plot randomly, either in a complete randomized design or in a randomized complete block design. So this particular design, CRD, is at the main plot level, and the split is at the subplot level. So we also assign levels of factor, the second factor, to the subplot randomly. And because the randomization occurs at both the main plot and the subplot level, we end up with 2 errors, which we have to estimate so that we are able to have the correct results. Okay, so when you are doing an analysis in split plot, pay attention to the main plot error and subplot error so that we have correct analysis. So I want to pause here and look at the chart in case somebody has questions. The Q&A. This one is telling me he hasn't received any molecular data. Materials and introduction, you mentioned it. I need it, please. We have not reached the level of molecular data material. We are going step by step. If we jump from split plot, we jump repeated measures, we go to molecular, we will leave people out. So we need to go step by step. We want people to understand. So you will excuse us, but okay. Let me go to the chart and see what the chart says. Split plot. What could be the possible source of variation for Anova if split plot design is repeated for 2 years? Okay, we are going to talk about that. Let me look at other. Please, Prof, a quick recap of the split plot. Okay. What could be the possible source? That one I've read. Split plot and factorial seem same. Could you explain the difference? Okay, split plot always related to area. Okay, sorry about the short interlude. I want to report who is disturbing me. Let me go back. The questions are that I recap on split plot. I said split plot. If I can go back to the notes where split plot starts from, I believe that factorial is okay. I said factorial is used if you have n levels of factor A and n levels of factor B, and your main aim is to find out the interaction between factor A and factor B. Now you find that factorial can be performed, can happen in a complete randomized design and a randomized complete block design. In factorial, we have one experimental error to use to test factor A, factor B, and the interaction. While in a split plot, we are looking at two sources of variation due to the differences in size of the plots. Here, we find that in split plot, we have a bigger plot called a main plot, where we are applying our factor A, and then a subplot, which is smaller than the main plot, where we are applying our factor B. Now, because of the difference in size of the plots, and also the replication at that level, we end up with two errors, two levels of variations, which we have to account for in order to get correct estimates of the means and also the standard errors of our predicted effects, treatment effects. So somebody says, how about if you have a split plot over time? Now, assuming you have factor A for main plot, and then factor B is time, we find that when our split factor cannot be randomized, the assumptions which I was going to talk about under split plot break down. Now, under split plot, we have factors. We assume, just like in analysis of variance, that factors for main plot and subplot are randomized. When you have time for a split factor, you can't randomize time, it is fixed. So then if we are measuring our response over time, the responses are going to be correlated. Okay, so the assumptions under split plot are that there are no correlations between the pairs of split plot within the main plot, and the variance is constant. So the variance of main plot 1 and main plot 2 is similar. And within main plot 1, the correlation you have subplot 1 and subplot 2, which are likely to be correlated because they are sharing the same environment. But split plot assumes that they are not correlated. And when that happens, if you find out that there is correlation within the main plot, there is what we call testing, using what we call Maliculi test. The Maliculi test tests to find out whether there are correlations within the main plot. If the p-value is significant, then we adjust using greenhouse geyser. Those terms I didn't want to bring them in, but I'm bringing them in so that you understand that when you have a correlation within the main plot, then you have to adjust those correlations using the greenhouse geyser. It is a test within split plot. And when that happens, if you find that actually you cannot adjust your analysis using greenhouse geyser, the p-value is also significant, then you go for mixed model. Mixed model now is going to model the structure of the data, is going to model the correlation and variances within and between the whole plots and within the main plots. So is that clear? Can I see in the chat the questions you asked me? How is split plot different from splint plot? Okay, you can have many splits as you want. You can have you can have main plot, subplot, then you split the subplot again. That is called a split. Okay? Then you can have 4 splits. So you have a split. Okay? But the more the design is complicated, the more the difficult in our interpretation. So make sure that you you have a simple design. Just like in regression, if you have a complicated model, a model with too many variables is not very good. So it makes you collect more data. Even for those people who come after you to use that model, will have to incur more expenses. So the simpler you are, the better. So always look for a simple design. And in a split, make sure that if you have 3 splits, for example, you have a main plot, a subplot, and a split of the subplot, you are going to have 3 error levels. Okay? So I hope that is okay. Somebody is saying that somebody has said that you will even have more work to do. Okay. What else did they ask me? They asked me about this is about the equation. This is the response, the overall mean. This is the effect of the block, the effect of the main plot factor. This is the first error at the whole plot factor. This is the subplot factor. And this is the interaction. Alpha beta is the interaction. Epsilon ijk is the error, the subplot error. And this is the observational error. The last, the gamma, I think this is gamma, is the observation error. Okay. Okay, so let me go to R, and we do practicals in those 2. Then we come back to repeated measurements and see what happens. Okay, so the script we are using is called follow-up split. That's what we are going to use for this session of practicals. As usual, you have to set your directorate. You have to run the library. Somebody was asking, do I have to run this library every time I open R? Yes, you have to run the libraries every time you open R. I was reading some literature, but I need to confirm that when you are in the lower right window and you go to packages, you can tick on that package and you don't need to reload it every time, but I need to confirm that. So please read about it and confirm. R is about discovering. You will find that you have 4 packages for one type, especially mixed model, split plot, repeated measurements. You can have like 6 packages analyzing the same design, because everybody is getting an easier solution of writing the code and making work simpler. So you find that I'll teach you that you use Agricola. Another one says use Gliss. Another one will use Due, So read as much as you can. Don't just take what we are telling you as the only thing you can do in R. No, R is about discovering, and we also discovering every day and learning every day as we run the analysis. Okay, so I encourage you to go back and practice and also discover more. So whatever we've not covered, you can always Google, read, and also listen to the audios. There are so many YouTube videos about split plot, repeated measures, about regression, so many that you can't finish. You just need to create time and read. So long as you know the method of analysis for your data, then you will be able to analyze your data and be good to go. Okay, so wherever we end, we are going to be able to catch up. Okay, so I am going to run the libraries, load them. Sorry about that. So there's one which I added called DO Bioresearch. It is also used for split plot, etc. For the different types of split you're talking about, it's under DO Bioresearch. It is called Analysis of Experimental Data. Dewey also, with that book I cited, they use the Dewey package. Agricola is also another author who came up with different types of designs and analysis. So you find that you can use any of them. So that's why I run them at once, so that I don't have to run them each time I want to use the packages. So I'm going to run, and then after running, I set my directorate. So I go to session, set directorate, or you can use the procedure that Dr. Helen gave you, whatever is convenient for you, please go ahead. So follow-up is my directorate, and I click open. I can see there are some comments in the chat and the Q&A. Okay, the chat. Script, please, Dr. Helen, please send a script to the participants. Okay. Script, yes, script is coming. Oh, for those, for the library DO, the script follow-up split, sorry about that. I forgot to tell you that you have to actually load that library, install DO Bioresearch before you can load it. That's why you're getting that error library package called that not found. Please, I give you 5 minutes. Use install.packages in bracket DO Bioresearch. Afterwards, then run it. It is going to run. Okay, let me see. Yes. What data set are you using? We sent out this morning, actually, before the lectures, they started the training. He's going to send all those data sets. The first one, I will use a data set called Factorial. So Dr. Helen is sending them again. So make sure you pick them from the chat. Okay, so already installed. So have you all installed the package? Can we go on? Okay, yes, let's go on. So we are going to read our data of Factorial. I've called it fact is the object, read CSV in quotes, double quotes, factorial.csv. So we read that data, just click run. So let's go together, click run. And head is for seeing the first 6 data set and also seeing how the variables are written in your data set. Sometimes I get the data sets from R, and how do I get them? When I'm reading my literature, they refer you to a particular package and they tell you this data exists in R. So you cannot actually know the data exists in R if you actually don't know what it does. So when I read literature, I find that there's a particular data set called OTS, and it is in R. So you can run the code, then you will be able to view OTS or any data set. Or even online, you can actually say, I want to download a data set called OTS, and they will give you a link, okay, for your practice. So if you want to know the column names for your data, this was just for practice, then you know that nitrogen is named with a lowercase crop, is the type of crop grown. So then we've already seen, if we use string, it tells us that nitrogen is an interval, crop is a character, and yield is numeric. So let's change nitrogen and crop to factor. So we go to the next. Hopefully I'm not very fast. Am I being very fast, or if the speed is fine, we continue? Can I see in the chat? If you say yes, I'll continue. If you don't say anything, I will still continue. Don't mind about bioresearch if it doesn't install. Due will help us, and Agricola. So if Agricola has run, we can be able to use those ones. So go ahead, please. Okay, so now let's run the, oh dear, the fact nitrogen to change to a factor. And also we run to crop. So we test to find out whether they've been converted. And it is true that crop has been converted. And also, let's see, let me check in my console. The factor nitrogen is also a factor. I'm going to run the factorial model. It is very simple. I've named it mod 3. That is the object of that equation. And we're using a function called AOV. Yield is a function of nitrogen. Yield is our response. And what are we testing? We want to test whether there is an overall effect of nitrogen on yield, as well as an overall effect of crop, the type of crop on yield. And does the level of nitrogen affect yield for the different crops? That is the interaction. Does the level of nitrogen affect yield for the different crops? That is the interaction. So we are testing 3 hypotheses in one analysis. That is the beauty of using. We are waiting for the PowerPoint as well. Okay, my colleague, Dr. Helen, will send the PowerPoint in a minute. That is the beauty of using experimental design. I find that if I do a survey, there's a lot of thinking to do when it comes to analysis. When you use an experimental design in your research, the analysis is straightforward. If it's randomized complete block design, you can't make it repeated, isn't it? So kindly repeat the 3 hypotheses. We are looking at, we want to investigate whether there is an effect of nitrogen on the yield of crops. And then we also looking at the effect of crop on yield. Does the yield vary from one type of crop to the other? Is yield affected by applying different levels of nitrogen to the different crops? That is the interaction. So you can put it in your own words. Does the different levels of nitrogen affect the yield for the different crops? Okay, and I'm going to run the model now, and then we interpret the results. So Dr. Helen, please send the script and also the data set and the PowerPoint. Okay, so let's run the model. Just put the cursor anywhere and run the model. And we've run the model. Then we run the summary of that model. So we are going to bring what we've run. So let me make this a bit larger. So this is the interesting part. When your model runs successfully, then you say, you sigh, you say, now this is done. Yeah? Paste the command of model 3, oh dear. Okay, let me paste the command of model 3. If it works, control copy. Control V, there we go. I have pasted the command of model 3. You can pick it and put it in your, if you have the data. Okay, so Dr. Helen, wherever you are, send the data set called Factorial, send the script and the PowerPoint, please. Thank you so much. And let's pay attention. We can recap the analysis, but the interpretation is the most important thing. We can know the R, you can know how to write the command, but if you don't know how to interpret, then you don't know anything, okay? So let's know both the command and R. So Dr. Helen is doing the needful, is sending the data set, is also sending the script, R script, and PowerPoint. Okay, so once you conduct an analysis of variance where you have a factorial treatment structure, you first look at the interaction. So we have nitrogen, and R represents the interaction with semicolon crop. So if you look at that particular row, we see that the p-value is small. It's smaller than 0.05. So if we have a small p-value, we have evidence to reject the null that there is no effect of the different levels of nitrogen for the different crops. That was our null hypothesis. The null hypothesis was that there is no effect of nitrogen on the yield for the different crops. But here we are saying that the results indicate that there is a low probability to support the null hypothesis. So we reject the null and conclude that there is a significant interaction between nitrogen and crop, implying that yield depends on the different levels of nitrogen applied to the different crops. Yield depends, or yield varies with the different levels of nitrogen applied to the different crops. So now, once you find a significant interaction, don't go to interpret nitrogen alone and crop alone. Nitrogen and crop alone are called main effects, and nitrogen ... crop is the interaction. Okay, so can I see in the chart? Is that interpretation okay? Can we go ahead and do some analysis? Can I see in the chart? Okay. Okay, so let's go to the next part. Once you have a significant interaction, the next analysis you do is to construct interaction plots, and that's what we are going to do. If you want to interpret nitrogen alone and crop alone, then when you construct the interaction plots, you'll be able to do that. So you don't need again to look at them separately, okay, from the interaction. So let's construct the interaction plots and see whether we don't get that information of nitrogen alone and crop alone, okay? So let's see. So put your cursor at the interaction, drawing interaction plots, and run. Error margins large, okay, that one I know it was going to happen. So when you get the red, don't panic. Don't panic, I need to reduce my zoom, so I'm going to zoom in. Zoom in again. Zoom in. Oh, zoom out. Oh, I was doing the opposite. Okay. Okay. Okay, so now let's run our interaction again. What about a seasonal effect? Say if the work is done for 2 years. If it's done for 2 years, then you'll also have time as a factor in your analysis, and you can have an interaction between time and nitrogen. So you want to find out whether the nitrogen you are applying actually varies over time. Does the effect of nitrogen persist over time, over the 2 years? So that's what you're looking at. Now, if you go beyond 2 years and you have 3, 4, Then that data becomes repeated measurements, and you need to use repeated measurement analysis. You have to look at the correlations, okay? Because if you run the correlations, you find that the measurements of yield over time are correlated. Is the time fixed or random? Time is fixed in that case. We can't randomize time, okay? If you get a data set stored, for example, in an archive, and they had time for 10 years, and you select five years, then time becomes a random factor. You see the difference? But if you're conducting your experiment now and you have 2 seasons, time is a fixed factor because you didn't have a random sample of time. You didn't have time on yourself to choose out 2. You only had 2 years. That's where you ended. That's where your resources ended. In comparison to somebody who has gotten data in an archive and decided to analyze only data for 5 years instead of 10. So he has a sample of 10 years, and then he takes a random sample of 5. Yes, you interpret the interaction as a change in the effect of nitrogen over the time period. Okay, any other query? Any other comment? Okay, let's analyze the interaction. Okay, so I'm going to run, hopefully also running, and we have our chart, our plot. I'm going to zoom in this plot. I'll also stop sharing in a minute and share. Would you do the same in logistic? Yes, you can do interactions in logistic. We can have interactions in logistic. So we have our interaction plot. And if there was no interaction, then we would have parallel lines, okay? Okay. My crop, part of it has been eaten up. I don't know how to make it large. Oh. Where is it? Sorry about that. Let me stop sharing and share. Okay. Zoom out before running the command. Okay, that's what he says. Okay, let me run again this command and see whether it improves, because my plot is hiding the legend. Interaction. Zoom out. Okay, there we go. Okay, then it is coming up. Yes, I think that is better. Let me. Okay. Anyway, okay. Let's see the interpretation. So I was saying that in case you find that these lines are parallel, then that shows there's no interaction. So here we first go to so we wanted to look at the effect of the main effects within the interaction plot. You can see that the crops are the lines. They are the lines you see here indicate the crops. And nitrogen levels are 0, 50, and 100. So at 0 nitrogen, no nitrogen applied, we can see that all the crops are performing so well. Okay? Now, as you apply more nitrogen, the yield is decreasing as you apply more nitrogen for all the different crops. So which crop is performing best? There's this particular crop here with a dark line is the one performing best. And it performs best at almost all levels, at 0, nitrogen at 50 and 100. What does this plot tell us about application of nitrogen? We actually don't need to apply nitrogen when we are planting these crops. Because when you look at all these crops, groundnut, soya, those are nitrogen fixing crops from the biology, the little biology I know. In that if you apply nitrogen, actually you'll be hindering them. Or the amount of nitrogen you apply should be minimal, okay? Because they are adding nitrogen, the plants, and you're also adding nitrogen. That's why you see they are performing so well when there is no nitrogen added, because they add nitrogen to the soil. But when you add nitrogen, the yield goes down, okay? So the different effect of the different factors over the different levels of nitrogen is what we call the interaction. So the crop has an effect on the yield of nitrogen. You can see different crops are behaving differently at the different levels of nitrogen. That is what we call our interaction. So if you want to interpret in terms of nitrogen, you pick the information from the interaction plot. If you want to look at the different crops, the performance, you'll pick the information from the interaction plot. So I'll stop sharing, go to the chart. Is there a session in R for principal component? You people pay attention of what is happening now. We cannot, you see, we can't change time. Time is fixed, okay? So we cannot go on the whole day. Even us, the brain will get tired. We have a specific time within which you can actually communicate. We can't do principal component today, but you have my email. Please, you can always ask me about principal component and we can dialogue. Those ones who want Anova principal component, email me. You can email me half of your data because data is sensitive, and then we shall see. But if I don't reply immediately, please don't blame me, because we've just done exams here at Makerere and I'm marking as well as teaching in the second semester. So I take off some time to do things. So please, if we've not handled some of the things, bear with us, but I can always spare some time as well and help. Somebody says, David is saying as well as being a mother. That is true. I have my two assistants here. You can't see them. Let me not waste time on that. Let's go back to R. Okay. Okay. So let's go and see. So you can actually run the interaction plots the way you are comfortable with. For example, if you can run it within this command, interaction plot, fact, $ nitrogen, fact $ crop, fact $ yield. You know, yield is the response crop. Crop is our other factor, and nitrogen is our factor. So if we run, we see that we have our plot similar to what we had, okay? So that is all about Factorial. Now let's go to split plot. So here we are going to split plot. Okay, yes. Okay. Hey, my colleague here was saying I was harassing her. Now she has started harassing me. Split plot analysis. Okay, let's look at split plot analysis. Let's see, let's at least deal with split plot. And we have an evaluation which we are going to give out. We need it to improve our delivery of the course and also organization of the course. So we need your views as well as teaching you. But as I promised, I'll spare some time for whatever we've not covered. And also, Reforum is organizing, I shouldn't be the one to mention it, but all these notes will be put online and you can access them. So you will be able to access the scripts for everything that we haven't done online. Okay, maybe with our voice or without the voice, depending on our forum's organization. So we are going to have this data set. Is called OTS data set, which I got online. It consists of 3 varieties randomly applied to the main plot and 3 levels of nitrogen randomly applied to the subplot. So this is a split plot design. It has only one split. So as usual, we read our data in. Let me reduce the amount of information in my consoler so that we can be able to see what is going to happen. So we've read our split and then run to see what the split data is. Okay. SP data was not sent. Okay, send it in the chat. Sorry, I missed that. I think I must have made a mistake. Oh, and my colleague Helen says it doesn't have. Sorry about that. I thought I'd sent it. Let me send it to Helen. Give me 2 minutes. I send the data quickly and then come back to do split plot. That must have been an oversight. Okay. I think I can send it in the chat as well. Isn't it? Here is the chat. So I'm sending the data for SP. That must have been an oversight. Thank you. The data set is called SP for split plot. So I'm sending it in the chat. Please pick it. And so please stop commenting. I am sending it the second time. Huh? I've sent only to you. You must have been the one who did it. Huh? Let me give them until come out. Okay, so I hope you've received the data set. Can I see in the chat, have you all received the data set? Have you downloaded it? So I'm going to give you 5 minutes to download it and also read it in your R command. Huh? Where is that? Where is that? Okay. So should I stop at 2:15? That send it again, please. They haven't seen it. Somehow I can't see it. Please stop commenting and we send the data again. Helen. I am back, so I believe that everybody has their data. Let's do this so that at least we can complete our split plot analysis. I'll stop sharing this. Then I'm going to share my script for split plot. Okay, so have you run this particular script? I haven't received it. If you're on the chat, please, you must have received. Dr. Helen is going to send it again. Please send the script and also the data. So for those, but we sent these things in the morning, yesterday, okay? So send also the script, okay? So if you've received, let's go on. So when you run your data and you say split, it shows you the data you have, then the structure str is for structure. Excuse me, sorry about that. So we are looking at the structure of the data. If you look at the console, let me magnify it a bit, magnify R so that we can make it bigger. Okay, so if we look at the console, we see that our data consists of replication, which is a character, variety is a character, nitrogen is a character. Replication represents our blocks, our variety is the main plot factor, nitrogen is the subplot factor, yield is our response, okay? Let's first of all convert, then we look at the hypothesis. So we go to split $sign replication as a factor, then we specify replication to convert to factor. So please run that. And I hope everybody, somebody says they've not gotten the script. They have got the script, but not the data. So please send it again. Thank you, Dr. Helen, for that. So we are going to run our split plot analysis. Pay attention. You can see that here we have different ways of running split plot. There's this one model with, then you have split plot is the data, split is the data, sp.plot is the function for analyzing split plot. I have highlighted it in blue. It's sp.plot. You can see that it is already bringing me that I should put in a block. If you look at your RStudio, when you highlight sp.plot, it actually brings you the command you're supposed to write. So you can see it says you put in blocks, put in the whole plot factor, subplot factor, and the yield. So now from sp.plot, we go to replication, that's our block, comma variety, comma nitrogen yield. Okay, let's run that. And we have our results. So the results are here. So if you look at the results, we have two levels. We have level 1, where we have replication, variety, and EA is the error at that level. It has none, none. Where you see none, none, R is telling you that you're not interested in the replication effect. You're actually not testing it. And you're not interested in the effect of the error. So that's why you see none, none there. But they have only highlighted for you what you're interested in. You're interested in the effect of variety on yield. So we have here, we are also testing 3 hypotheses at a go. We are looking at the effect of variety on yield. Please paste the command of split plot in the, okay. I don't know what is happening, but let me paste it. Control copy. There we go. Do you have it now? Okay. So that is the first way. So I was looking at the interpretation and I was showing you that, you see this analysis is quite different from Factorial. Factorial, we only had 1 error. Here we have 2 errors. Okay. So we have the first error called EA at the main plot level, and we are interested in the effect of variety on yield. So the p-value is big. You can see it is 0.28, bigger than 0.05. So we have no evidence to reject the null and conclude that actually the yield does not vary among the different varieties, or there is no variety effect on yield. So we find that variety A almost has the same yield as variety B as variety C. So let's go to the subplot level. I'm going to highlight it in blue. The subplot level, we look at the interaction. No, we are not talking about the effect of nitrogen on variety. We are looking at the effect of nitrogen alone, and there where you see variety, semicolon, nitrogen, that is the interaction. The interaction says the effect of the different levels of nitrogen for the different varieties, okay? The SP function is not working properly. Probably you didn't load DO. That SP works for DO bioresearch, okay? That's why I ran all of them, and I told you at the beginning that you install the package DO bioresearch, then load it, and SP function will work. Okay, so then if it's not working, let's wait for the alternative, which is also the same, giving us the same results. So let's interpret this. We are looking at the interaction and it's non-significant, meaning that yield is not affected by the different levels of nitrogen for the different varieties. But the main effect of nitrogen is significant because the p-value is small, smaller than 0.05. So yield is actually affected by the different levels of nitrogen alone. Irrespective of what crop you put in, the different levels of nitrogen will influence the yield that comes out, okay? So if you find a significant main effect, you go ahead and do the LSD, the pairwise comparison tests, you remember, okay? So you can go ahead and find out which particular variety actually is giving us those differences with the LSD information we used in the Anova. So when you're doing the LSD under split plot, be careful to actually specify the correct error. EB is the correct error for testing the LSD in that particular case, okay? So let's go and look at another way of doing the one which I'm going also to paste. Before I do it, I'm going to paste it, Control copy. I'm pasting this part also in the chart using function AOV, okay? So in function AOV, we put yield is a function of replication plus variety times nitrogen plus the error term. Now you see this error term here. The error term being specified here is the error term for the main plot level. It is replication over variety. It is the error term for the main plot level. It's what you want to specify so that the Anova can give you the correct analysis. So let's run that and run the summary. And let's look at the analysis, the output. Huh? Pardon? Okay, so when we look at the Anova or AOV function, now AOV works under Dewey and Agricola. So I want to tell you the different packages and different functions they've used in R. So once you run Agricola and Dewey, AOV will run. So for sp.plot, it runs under DO bioresearch package. Okay, so you can see that under the data, the analysis, you can see it as separated. We have two analysis of variance. This top part, which is the main plot, and we see the results are similar to what we got before. So the same interpretation again, okay? So we also look at the bottom part. It's the same results. So what do we want to report? We can report all the results now because the interaction is non-significant. You report a non-significant interaction. Your P is equal to 0.717 degrees of freedom, and then the F value, okay? So you also said that implies that the yield does not vary with the different levels of nitrogen for the different crops. So you don't need actually a combination of the two to have an effect on yield. However, yield is significantly affected by the different nitrogen levels. In bracket, P is equal to 0.0108, F value 10.22 degrees of freedom you specify. You are writing your project now, okay? Okay, so let me see in the chat. Is that interpretation okay? I am going to have one data set that we are going to analyze with you people. And once we do that, I want you people to interpret that particular data set, okay? I'm going to get interpretations in the chat to test whether you people have understood, because now after today, we will meet again online using email, okay? Ladies and gentlemen. Okay, I can see that you're fine. So I also sent you a data set called seed. In this data set, we have blocks. In the previous data set, the design, if I can ask a simple question, what was the design? It's split plot design, but was this a CRD? Was it a randomized block design? Can we have answers in the chat? What design was it? It's a split plot design. Yes, somebody, Simon said CRD. Good, 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 good. Thank you. All the answers are correct. It is a CRD and it has a split plot within that, okay? So in this case here, once you see blocks, that means it's going to be a randomized complete block design. But remember that if there's unequal replicate, then that is called incomplete randomized block design. Now that book, which I have referred to in the notes, has all the types of design. So if you want to read about incomplete block design, go download that book. It is free of charge. Email, then these things of academics, ResearchGate. If you're part of that, you'll be able to get it freely and download it. It has all the designs we are talking about. And I think even those who want molecular biology designs, they are also there. The lattice, the alpha lattice are also there, that language, okay? But I believe that in the future, if God allows, and also Forum has resources, they will put up another follow-up where we have molecular biology coming up. Somebody says he has seen my publication in ResearchGate. Thank you. Okay, let's do this analysis quick. So let's read seed data. I hope you have the seed data. Oh, the book is in the PowerPoint. Please, if you have the PowerPoint, it is there. Okay, so read the data set in, print it if you want. Look at the structure. Cultivar, we have 64 observations and 4 variables. In this data set, blocks are interval, cultivar is a character, and seed chemical is also a character. So this seed chemical was applied to the seeds to look at their yield and also their germination rates. So the different rates of germination and how they grow after the germination. So they apply the different chemicals, okay, to the seed. Then, because now we have interval and character, let's change blocks to a factor, cultivar to a factor, and seed chemicals to a factor. So if we run those lines and check, you can check actually, go back to string and check whether you've converted them, and it says yes, factor, and numeric, okay? Margaret says third follow-up will do with multinomial logistic. Thank you. That depends on Forum, not me. I will not say anything. Please mention it in your recommendations. The recommendations that you actually write up in the evaluation will determine what will happen. Okay, thank you. Oh, I have 6 minutes. That is Helen talking. You know, she took my time. Now she's also telling me. Okay, let's run the model very quick. Using the OF, I've chosen the OF because it gives you a neat analysis. And remember, I've specified my error term using block over cultivar because that is where I want the error term to be specified. So when I run, I get an output. Okay, so let's do this. So you can see on top, we have the main plot factor. Yes, cultivar. And it is significant, meaning that the response of cultivar after they've applied those chemicals, there's a significant effect of cultivar. Cultivar affects the yield. Okay, there's a significant effect of cultivar on yield. Then if we look at the lower part, now it's your turn to interpret. I want comments in the chat. How do we interpret the results for the lower table where we have seed chemical and the interaction between cultivar and seed chemical? Let me see volunteers. Which PowerPoint has the book name? The PowerPoint we are using now, it is called repeated measures. I think it's called repeated, yes. It has the name in there, the name is there. Somebody said significant. What is significant? I want you to write seed chemical has no impact on cultivar. Are you sure? Okay, let's see, seed chemical. Germination rates are dependent on cultivar types and the kind of chemicals applied. Excellent. That is very good, Sarah. Any other? Nope. I react. Okay. Cultivar affects germination. Okay. Okay. I need more comments. Can you please interpret the results? I need to see in the chat. Okay, so cultivar are more significant. Okay, there was a significant interaction. Germination rate does not vary with seed chemical, but varies significantly with interaction of cultivar and seed chemical. The interaction is significant. Yes, there is a significant interaction between seed chemical and variety, indicating that when you apply the chemical onto the seeds, then there is an effect on germination and also the growth. Yes, germination is significantly influenced by the, no, germination, yes, is significantly influenced by the seed chemical and the cultivar. So you find that when you apply a particular chemical to cultivar Clinton, actually the cultivars, there is Clinton, there is another one. So if you apply, let me say, Agroc X to Clinton, you will get a different result or effect when you apply another seed chemical to the same cultivar. So germination rate depends on both variety and chemical. Great. That is good. It makes me feel better that actually today has been a success. Even if I don't give you an exam, I already see that you're doing a good job as you're paying attention. So we have a significant interaction, and normally when there is a significant interaction, ignore the main effects and do construct interaction plots. So even here, let us construct our interaction plots, okay? Okay, so here I have interaction plots. You can use either way. So let's run the interaction plots. So I'm going to leave this out so that we can see the interaction plots. So let me zoom out and share that. Is my time over? 1 minute. Oh, is this my interaction? Okay, 1 minute, I'm told. Okay, we have the interaction plot here. You can see that they are showing they are not parallel. You can see the different cultivars drawn for you. On the vertical, we have the mean response, and we can trace which cultivar is performing well at which seed chemical. We have this dotted big dots is called Agromax. Then the small dots, this particular, the one which is on top is called Serena, then Clinton. Okay, so you can look at, there's a lot of information there, and actually you can go in R and make your graph more beautiful than mine, and you'll be able to copy, paste it in your Word document and read and write a lot. So which particular cultivar is performing well, and at what chemical? It is the cultivar called Branch. You can see Branch is performing well at all the types of chemicals. Which one is performing worst at all types of chemicals? It is Vicaland 1. And which is the next best? It is Clinton. I don't know, Clinton must have given money in to this experiment. So Clinton is the other cultivar performing well next to Branch. So you have a lot of information here, and pictorial graphs give a lot of information to non-statisticians. So let me look at the Q&A. Good morning, doctor. I haven't received, no, let me see more questions. Use a Gigi plot function for interaction plot, please. No time, but you can actually practice that. And if you fail, Google, let me see the chat. Not yet, Dr. Helen, be kind, please. Please do the mean separation. Not now, please. I will not do the mean separation. But as I said, I want to thank you for being very good participants, and you've been patient with us. We've been grilling you for the last 6 days, every time R, every time interpret, but the link has been sent in. Please, we need those comments. Click on the link and answer the questions. Answer the questions, we need them. We thank you so much for being you need certificates. Dr. Nyararo from Ruforum will comment on the certificate. I do not have evidence to reject the null, that there is no certificate or there is a certificate. Yes. Happy Independence Day. Thank you so much. The P for chemical is 0.058. It is not significant if you're working at 5%. Okay. So please, can you share the link again? Please stop commenting and let's answer the link. Let's answer the link. I am so grateful. I need those comments. Yeah. Please share the SV file. I will send it on your emails. Don't worry. We will send the SP file. Okay. I want, please, we are giving you, how many minutes are you giving them to answer? 7 minutes. Paste the link again. The link is, keep pasting so that they can answer. So those who are addicted to Q&A come to the chat and answer. No link, the link is there. The link is there. The link is there. Paste the link. Dr. Helen, don't get tired. Just keep pasting so that everybody know where to be seen. Oh my God. Okay, I am going to mute myself. Maybe I wait until the 7 minutes end. But, I have said I have no evidence to reject the null, that the certificate is available, but I think I have already done the analysis and I have a p-value which is non-significant, so it appears the certificate might be there. It is going to be there. I believe so. Don't crucify me if you don't see your certificate. Yes. Great, the p-value is 1. Dr. Nyararo is going to confirm that p-value by doing a mean separation test. So don't worry. Yeah. Okay. So the minutes we have, how many minutes? 1 minute to go. Oh, 6 minutes, sorry. I am moving ahead of the time. 6 minutes. They don't want to reject the null. So I will leave you to concentrate and you answer those questions. Please don't go, don't log out. We are, Dr. Nyararo has a few comments. We are going to close. Don't go, please don't go. Wait for a few minutes. At 2:20, Dr. Nyararo will be closing the session, but I commend you for being very, very good participants. I have said Dr. Nyararo will do the means comparison test on certificates and will give you the results immediately, so don't worry, the results will come, and I believe she has better answers than me. Thank you. Okay, we have 4 minutes. You want to order before they bring my phone. Gabby, bring my phone. Please make sure you fill the SurveyMonkey questions. There are very few questions. We need your comments. We need to improve. We need to do a good job so that both of us benefit. You and me, we need those comments. So please comment honestly on them, and then we can see how those comments can improve our future training, our delivery, you know. Okay, so please do that. Can you go ahead and talk? Me, I want to order. I order. Oh, okay. Okay, so 3 minutes left, but I would like to hand over to Dr. Runyararo of Ruforum to start doing the means comparison test of certificates. There she comes, so I'm going to mute myself.
Thank you, Professor and Doctor, for this wonderful training. I'm sure the participants have really enjoyed the delivery of the training. I can see a lot of thank yous in the chats. People are grateful for the delivery of your work. But before I close the meeting, I would like to allow my colleague, Ms. Sauma, to say something to the participants before we officially close. Thank you.
Thank you very much. Good afternoon. Thank you very much, Dr. Ngararo. Thank you, Professor and Dr. Helen, for really a very insightful lesson and sessions that you've given to the participants. And we really would like to thank you also to the participants, give a vote of thanks to all of you for being really very participatory during the course. And that has also encouraged the trainers to give you more of what you need. So we just want to thank you. So from the Forum Secretariat for being there for the training. And we hope that you have learned a lot and that you are going to use those trainings also in your career to do your data analysis and everything and do your quality papers. So thank you. Over to you, Dr. Ngara.
Thank you so much, Selma, for those comments. Colleagues, I want to thank all of you for taking time to be part of this training. I want to thank our facilitators so much for taking time to be here, especially this day. It's a Uganda Independence Day. They should be home with family, but they did not take that into account and managed to come and take us through the training. So Professor Tumwewaze and Dr. Namaweje, thank you so much. And the participants, thank you. On the issue of certificates, this is a follow-up training. And we were not anticipating to give certificates because it's the same training which you had and most of you got certificates. So would it make sense to have 2 similar certificates of the same training? Well, that's what we had thought of here at Forum Secretariat, but we are going to have an internal meeting with the superiors to see if we can actually have those certificates. So we shall be in touch. Thank you so much. Enjoy the remainder of the weekend. God bless you. Bye.
Bye-bye. Bye-bye. Bye-bye.